This video is for Lab 13, the final lab of the course. In this lab, you are going to design, build, and test a one-channel electrocardiogram. Now, the basic idea here is to do an entire design from beginning to end. So, what does that mean? Well, to start with, your goal is to produce a plot, somewhat like this one, using signals from your own heart. So, what does a full design mean? It means you've got to start with what are the specifications. You've got to come up with your own specs. What sort of signal are you going to have coming in? What sort of signal do you have to have going out to your data acquisition system? What discrepancies are there between these things? The analog electronics you design have to be sort of the matching between what comes out of your sensors and what goes into your data acquisition system. So you need to worry about things like, all right, this is a single-ended or differential signal. If it's a differential signal, how big is the signal? How big is the common mode? Because obviously you want to make sure that you take only the signal and not the common mode noise. And that controls things like what's your first stage got to be? There may be limitations on the gain based on avoiding clipping due to common mode problems. So figuring out the overall gain you need. What do you need to get from one end to the other? How much of that gain can be in the first stage? How much can be in the second stage? Do you need filtering? What sort of filtering do you need? Do you need to get rid of a DC bias? Do you need to get rid of 60 hertz noise? Do you need to, how high a frequency do you need to go to? How low a frequency do you need to go to? All these things are things that you need to consider in doing your design. And the best way to put all these sort of design constraints together is to make yourself a block diagram that says, okay, these are the different stages of the design, these are the different blocks, this is what each one of them does, these are the signals that can communicate between them, so that all the pieces are there in place. Once you've got your block diagram all done, then you have to design the individual blocks. How are you going to build the first stage? How are you going to build any filtering you've got? How are you going to build second stage if you've got one? Do you need to have a VREF generator? All these considerations go into making your schematics. Once you've got your schematics designed, then you need to build the thing on a breadboard, a stage at a time, and start testing things. Now, sometimes it can be difficult to do all the testing with real signals from the EKG leads. So the EKG electrodes, you only have a limited number of them, and they can be uncomfortable to wear, so you probably don't want to start using them until you've got something that you think has got a good chance of working. So one of the things that's often done when you've got expensive to collect data, in this case it's not extremely expensive, but still you might not want to be doing the actual EKG for all your testing. The thing to do with expensive data is to emulator, to produce something that produces signals like the signals that you're going to have, but are cheaper to produce. And here's an example of how you might build such an emulator. You can take pair of function generator channels from the Analog Discovery 2, feed them together into this circuit, which basically averages them, scales them down, so that if you look at this thing, you can look at, well, what is Vout1? Just take a voltage divider formulas, and you've got V in1, V in2, you've got Vout1 as one formula, Vout2 is another formula. You can make a differential channel here that has a very small differential signal, and you can set the common mode signal to be nothing or as large as you want. So this is a way you can test, hey, am I really rejecting the common mode signal? What is this thing doing? So I recommend, once you've got, say, the first stage of your system built, that you make an emulator like this and check to make sure your first stage has the gain you expect, if it does any filtering, that it does the filtering you expect, and basically that everything is behaving the way you want it to. You can set this thing up to have the size signals that you would expect to see coming out of the EKG electrodes, and also frequency ranges and stuff. You can use this with a little bit of care. You can use this this thing with the network analyzer to actually plot out the response of your amplifier as a function of frequency. Okay, so once you've built and tested stuff on your breadboard, basically testing stage at a time, starting from the beginning and working towards the end. Once you've got something that you think is working, then you need to hook up the EKG and test it with that. And here from the textbook, I've shown the way that the electrodes are arranged. Notice that there's two electrodes right under the collarbones, sort of on the hollow there where there's not much muscle, because the muscle signals from the pectoral muscles can really wipe out the heart signal you want to see. So you want to be relaxed while you're doing this thing. You can actually experiment with what happens if you tense the pectoral muscle, see what happens to your signal. It really is quite dramatic. But there are three different leads here, which are different ways of arranging the differential channel. If you're doing it left arm minus right arm, that's lead 1. And that's the one that I was showing in this previous one. That was a lead 1 plot. And as you can see, it looks like a pretty classical EKG signal, at least on me. For some people, that signal doesn't look quite the same because the heart doesn't have that much of a horizontal motion in the initial depolarization wave for the ventricles. And so the R spike isn't that nice, clean, single spike. If you get that, then try lead 2. That is left leg minus right arm. So it's looking diagonally across the heart instead of horizontally across the heart. And that diagonal path is more likely in many people to have the clean depolarization wave. As that depolarization travels along the septum is often oriented along what is the lead 2 direction. And of course, you can also use lead 3, which is looking vertically, left leg minus left arm. So it's looking for a downward motion. And one of these three is likely to give you a good signal. So you can play with all three and see which one. It's just a matter of rearranging the clip leads to get the different leads. Okay, so if you get the EKG signal and working everything with your breadboard, save all that data, get your GNU plotting working so that you can get a nice plot like this. You want to make sure that your output is in millivolts, that is the millivolts at the electrodes. So you have to know what the gain is of your amplifier and compensate for that. So if your output is 1.2 volts, what does that mean? Nobody knows. But if you take that, what's the difference from your VREF? All right, now I've got it divided by the gain of the overall amplifier. That tells me how big the differential signal was coming in. That's the thing that you want to report in an EKG. So make sure that you get the GNU plot script set up so that you report the electrode voltage, not the output voltage of your amplifier. Nobody cares what the output voltage of your amplifier is. What they care about is what's the signal of the electrodes. Similarly, make sure your time base is in seconds. It's nice if you can do the standard grid for EKGs, which is a 5x5 square. So you can see there's somewhat heavier lines every 5 there. And the 5x5 squares, each of the little squares is 1/10 of a millivolt high and, 40 milliseconds wide. And that's a standard grid that cardiologists have been using for decades now. And so if you can produce something that's in the standard grid, it looks a little bit nicer. Okay, so you've got your breadboard done. You've got your plotting all set up. Are you done? Well, not quite. Because you want to build a permanent device, not just a breadboard. And that means soldering. So what you're going to have to do is going to have to take your schematic and do a layout for it. This is the same sort of layout that you did for the microphone preamplifier. Figure out which amplifier, which op amp on the quad op amps is which for your wiring. Color code your wires so that you can easily debug it if there's a wiring mistake. You don't have just a tangle that's impossible to figure out what's going on. Do a careful layout, then put put in the components, building, the ones closest to the board first, so put in the chip first, and then the resistors, and then the wires and capacitors, and finally the screw terminals. So building up to make it easier to do the soldering. Build all that, and again, you can do some of the building a stage at a time. You could build the first stage and say, okay, if I got that working. And it's easier perhaps to do that if you haven't got all the other components and wires interfering with your ability to test that stage. So get a nice layout, get the soldering done, and then do the testing over again. Get another trace like this one, working with the soldered board. And that then will be your completed project. You'll have a working one-channel EKG. You can do whatever experimentation you want with that, as long as it's ethical. And that'll be finishing you up for the course.